20 billion messages a day requires a system architecture that behaves differently than almost any other application on the public internet. At peak hours, that daily volume translates to roughly 700,000 individual messages processed every single second. The engineering requirement is absolute fidelity. This throughput must be achieved with zero data loss, even across highly volatile mobile networks. Standard web application architecture is incapable of maintaining this volume. Scaling to these heights requires abandoning the stateless nature of the web to manage the specific connection state of every active user. This illustrates the standard stateless HTTP lifecycle. A client requests data, the server responds, and the connection is immediately severed. To simulate instant messaging over HTTP, the client must repeatedly pull the server every second to check for new data. Every single check requires a brand new TCP handshake and a complete exchange of HTTP headers. Multiplying that overhead across 500 million users creates a massive computational tax before a single message is even delivered. Server connection pools become exhausted, and latency spikes out of control, causing the system to stall under the weight of the handshakes. True real-time delivery is unreachable as long as the server remains passive, forced to wait for the client to initiate every transaction. Solving the polling problem requires a shift to stateful, persistent connections. This is the WebSocket protocol. It begins with a standard HTTP handshake, but the connection is kept open, upgrading into a persistent TCP tunnel where data can flow continuously in both directions. Because this tunnel remains open, the server can actively push incoming messages to the client at the exact microsecond they arrive. Maintaining millions of these open WebSockets is the specific engineering reason messaging applications feel instantaneous. Holding millions of open WebSockets requires thousands of individual chat servers running concurrently. This creates a routing dilemma. If user A is on server 1, how does the system know which specific server holds the open WebSocket for user B? The system uses a centralized session tracker to bridge the gap between these servers. Redis, a high-speed, in-memory data store, is used to map every user ID to their current server ID. When user A sends a payload to server 1, the server immediately queries Redis. Redis returns the target address, allowing server 1 to forward the message directly across the cluster to server 89. Server 89 then pushes the payload down the existing WebSocket to user B. Instant messaging across distributed infrastructure relies on decoupling the connection state from individual servers and centralizing it. Mobile networks are inherently unstable. Users frequently enter dead zones, which severs their WebSocket tunnels. The system must have a protocol for when their Redis lookup reveals a user has dropped their connection. This is where asynchronous decoupling occurs. If user B is offline, the message is diverted into a holding queue. The message is buffered in the queue and simultaneously logged in a high-write NoSQL database for permanent storage. When user B regains service and establishes a new WebSocket, their Redis state is updated to online. The queue automatically detects this state change and flushes the buffered messages to the new chat server. These asynchronous queues act as functional shock absorbers, ensuring zero data loss regardless of network volatility. Processing one-to-one messages is simple compared to the load generated by a 500-person group chat. This is the fan-out bottleneck. A single inbound payload requires a server to execute 500 simultaneous outbound routing queries and pushes. Executing this synchronously would freeze the chat server, blocking traffic for every other user on that machine. Smart systems use dynamic routing logic. Small groups are processed directly, while large groups use a dedicated asynchronous pathway. For large groups, the payload is immediately offloaded from the chat server into a queue. Dedicated worker nodes then execute those 500 outbound requests in the background, keeping the primary chat servers responsive. Scaling distributed systems effectively requires identifying expensive linear operations and shifting them into background processes. This distributed backend architecture maps directly to the familiar checkmarks in your chat interface. A single tick indicates the payload wrote to the initial server and database. A double tick means it traversed Redis, reached the target server, and pushed through the recipient's WebSocket. The blue ticks represent an acknowledgement payload firing backward to confirm UI interaction. This journey requires database writes, asynchronous queues, and multi-server routing, all completed in milliseconds. This architecture achieves global speed by shifting from a model of reactive requests to one of persistent asynchronous distribution.